Welcome back, guys. Now we are going to discuss on the Cauchy-Tucker conditions. Of course, at this point, still devoted to solve linear optimization problems. Consider we have a primal and a dual form. If you go back to my video, to the other videos, you're going to see that there is like a small difference in between those two forms. That's related to the operators over here. That's also related to one of those variables in one of the forms. Just go back and compare, please. That's part of the homework. Okay? That's why in the previous videos I used our Lagrangian functions. We're considering always the minus sign when plugging the constraints. Okay? But no problem for now. Just consider those two forms, primal and dual form. Those are completely right and written considering all the operators they should consider. At this point, we are mature enough at least to understand the Cauchy-Tucker conditions. So, having the primal and the dual problems, what is the Cauchy-Tucker conditions? Those conditions are basically, I need to satisfy the primal constraints, and I need to satisfy the dual constraints, and I need to satisfy something that plugs all two constraints, all two sets of constraints together. That's what the Cauchy-Tucker conditions ensure for us. Just consider again, remember those two problems, and now we are going to put one on one side, on the other. This is again a table as we used before to understand how variables affect constraints and how constraints affect variables. Actually, I brought this table because it's going to be even easier to find the operators and the space of variables for you guys. But those problems are here, same problems as before. Okay. How could I build up the Cauchy-Tucker conditions? The first Cauchy-Tucker conditions is called the primal feasibility. If you go back, you are going to see that those are the constraints we have for our primal problem. That's why they are referred to as the primal feasibility. Take a look, AX greater than or equal to B, X must be greater than or equal to 0. Going back, take a look here in my primal problem, AX greater than or equal to B, X greater than or equal to 0. Okay. Next, the second set of conditions we have is referred to as the dual feasibility. In this case, our dual feasibility is not represented in terms of the less than or equal operator, but in terms of the equality. Remember, going back, again, we have WA smaller than or equal to C, and W greater than or equal to 0. At this point over here, when I solve I was using like Lagrangian multipliers to find the dual form for a maximization problem. So we found the minimization, and then in those previous videos, I did the opposite later. I just took the minimization problem to find the maximization. But actually, when I solved, I think you guys remember, I used the minus sign multiplied by some x of this function, this constraint, and then we found together some equal instead of smaller than or equal. This is actually the complete solution. That was just an approximation, so we could solve together. So that's why that minus is going to affect and bring this operator instead of an equal. Okay, it's going to be smaller than or equal. Actually, if we're having like a full course on optimization, the correct solution was to consider the minus sign while plugging constraints into maximization problems, and the plus sign while plugging constraints into minimization problems. I can show you that. Yeah, maybe I think I have something here. Let's see. Oh yeah. That's a quite simple. Of course, this is just Wikipedia, just of course for a reference. But you guys are going to find something like this. Oh, is it here? Oh yeah, it's in here. When you are, let's like this. When you are maximizing something, you are going to use the minus sign in front of the constraints you are plugging. Those are the constraints. And for minimizing, you're going to use the plus sign, but that will affect those operators in the constraints. At this point, I'm not worried about that. I'm just going to consider the Courage-Tucker, but I felt like it was nice to tell you about why this was different from the previous formulation we had. Okay, so giving next step, you're going to see that this is basically the dual constraints. Take a look at the dual constraints. WA smaller than or equal to C, but if I plug a slack variable here, S, I can make like plus S equals C, but S has to be greater than or equal to 0 because I'm going to sum up something to find C to make it equal to C. It cannot be negative. That's why we have this. S is greater than or equal to 0, a slack variable being summed up over here to make it equals to C. And W was already greater than or equal to 0 over here, as you've seen. Okay? So this second constraint is called the dual feasibility. What is this third constraint? Actually, this third constraint is basically the result of if you guys just pay attention, you can notice that this is actually a way of connecting the two spaces we have here. Here we have a primary space, the constraints to the primary space related to the primary space, and the constraints related to the dual space. Again, when I plug these constraints, or this, actually this constraint, into my Lagrange multiplier for the primal problem, you remember I multiply this by some Lagrange multipliers or Courage-Tucker multipliers. In this case, Courage-Tucker because it's greater than or equal. It's an inequality, of course. If I consider that to be W, you see that I can multiply when I make this equals to 0. Take a look. That's exactly what's written here. I'm just trying to tell you that if this constraint for the primal problem multiplied by some W, which is related to my dual variable W over here, take a look, this has to be equals to 0. And that makes something necessary. That makes some slack variables multiplied by vector x equals to 0. That's something that comes up later when I do the opposite on this. When I multiply all this by x and solving this for x, I'll have this as my complementary equation over here. All this together, all this row together is referred to as complementary slackness. So the primal constraints must be satisfied, the dual constraints must be satisfied, and of course the connection in between the constraints must be satisfied. That's the same as saying that with this third row that I'm connecting both spaces, connecting the solution of the first with the solution of the second space. If you guys are really interested and want to go into the details on that, please go to this book by Bazara, Jarves, and Chirali, which is called Linear Programming and Network Flows. It's a very good book. Around page 264, you're going to find that's I think that's for the 4th edition. You're going to find some additional information on how to find this. Okay? I can also share later some information on that, but the book brings it, all the proof for those three conditions, considering the prime and the dual problem and how they connect together. Okay, so at this point, I'm really interested in applying the Karush-Tucker conditions in a graphed problem. Consider this problem. Problems here. First, one of the constraints is this one, and the other constraint is this one. Two constraints. Of course, my x1 has to be greater than 0, greater than or equal, and x2 greater than or equal to 0. So I have this feasible region defined in blue. How could I solve it? I could just apply the Karush-Tucker conditions. That's something I want to show you now. Consider this vertex 0, 0. If I apply it in my first equation, or inequation in this case, of course, set of equations, the first row, given x equals 0, 0, I will have a multiplied by vector 0, 0, it must be greater than or equal to b. Actually, this first is satisfied if I multiply this a 1 minus 2 by 0, it's going to be 0, and minus 1 minus 1 by 0, by vector 0, it's going to be 0 as well, and 0 is greater than or equal to minus 4, as you see here. Okay, so this first condition is satisfied. X must be equal, greater than or equal to 0. That is also satisfied over here with this first. So I'm just considering this first corner, this first vertex, to assess if it provides a solution for me. Let's try to apply this on the second and on the third Karush-Tucker conditions and verify if it satisfies those two other conditions. Okay. Geometrically, and I just noted here for you guys, we notice the two constraints are non-binding at this point. What means the two constraints are non-binding? If you go back to some of my videos, you remember that to be binded, I need to touch the constraint. I need to have the solution on one of those constraints. If I have this point, 0, 2, I will have this solution, this constraint affecting my solution. So it is binded to my solution, or connected if you prefer. If I get this point, 4, 0, I have one of the constraints binded to my solution. If I get this point over here, both constraints will be binded. Okay, but if I have this one, no constraint will be bounded because those constraints are here. Okay, so this has no non-binding constraints. Of course, as W is related to the other space, to my dual space for this problem, that basically means that W's are equal to 0. I have no constraint, no relevance for the first constraint, no relevance for the second constraint, because I don't touch those constraints in that particular point. Okay. When I solve this for W, W is of course greater than or equal to 0, that's satisfied. I can plug W here with my matrix A. A is here 1 minus 2, minus 1 minus 1. I can multiply, of course, by W. This is going to be, of course, 0 because W is 0. So S will be equal to C. C is, in my case, minus 1 minus 3, as you might notice here. So my S will be minus 1 minus 3. My problem here is my slack variable all slack variables have to be greater than or equal to 0, and that's not the case. So I can just conclude that this first point 0, 0 does not satisfy my solution. What I suggest you guys to do, try to solve for this point 0, 2, for this point 4, 0, and then for 4 thirds, 8 thirds. I'm going directly to this point, 4 thirds, 8 thirds. In this case, W has elements. W cannot be 0. I mean, no scalar value inside that vector W can be equals to 0 because I'm touching both constraints. So it is different of 0, of course. So just consider the constraints, the conditions here, my primal problem over here, and let's apply for this point. Just stop the video here, try by yourself, and then you go back, come back to the video, okay? Okay, so just giving another step. Of course, if I am touching that particular problem, we're going to have some value for x1 and for x2 that's greater than. Take a look, go back. x1, which is in this axis, and x2 are going to be greater than 0. Both are going to be 4/3 x1 and 8/3 x2. That basically means that when I multiply x by s, I need to have a 0 as a solution to satisfy the third Cauchy-Quintet condition. Therefore, s has to be a vector with 0, 0. Otherwise, I will never have the 0 as a solution. So s will be 0. Of course, this s1 and s2 are the two scalar values inside the vector s, composing it like this, 0, 0. Okay? So if I plug that, of course, this s equals to 0, 0, in this second Cauchy-Quintet condition, I can solve WA equals C. Solving WA equals C, I will have the first scalar of vector W, I will call it W1, and the second as W2. So I will have, of course, the solution of W multiplied by A, and A is this matrix. +1, -2, -1, -1. Okay? That's matrix. That's my matrix. When I solve for that, W multiplied by that, I'll have W1 minus W2 equals the first value of vector C, which is, going back, -1, and -2 W1 minus W2 equals -3. -3 is the second value of my vector C. Remember, my vector C is actually the coefficients that I have for my problem, for my objective function, sorry. So -3. When I solve W1 for W1 and for W2, I will find positive values for W1 and for W2. That's a good point. Why that's a good point? If I go back, again, s can be greater than or equal to 0. In this case, they are equal to 0 because I'm touching the constraints over here. W's are greater than 0, actually. They have positive values. And I am satisfying this condition as shown before. Okay? So this was satisfied, completely satisfied. This part, s multiplied by x, was also satisfied because I just assumed s to be equals to a 0 vector to make this product possible. Okay, and from that I define s over here as the 0 vector, having two scalar values. Okay, of course, from this I can give another step. So s1 and s2 are equal to 0. My x1 and my x2, you have those because we just graphed. That's 4/3 and 8/3. Our w's are 2/3 and W2 is 5/3. If you apply those values onto all those conditions over here, you are going to verify that all those were satisfied exactly on this point. Okay? If you apply here, no. If you apply here, no. If you apply here, no. The only point that satisfies the Cauchy-Quintet conditions is the solution point. So just getting back in your mind, it's so interesting to apply the Cauchy-Quintet conditions on candidate solutions because you can find what is the candidate solutions that indeed solves my problem. That's why we use the Cauchy-Quintet conditions to find which vertex provides the solution for my problem. I'm going to give another step. Now I'm going to interpret the Cauchy-Quintet conditions from a different perspective. Graphing my problem again, That's my problem, the same feasible region. What could I do? I could just compute the gradient vector for my objective function, the gradient vector for my first constraint, the gradient vector for my second constraint, and the gradient vector for my variables. If I compute the gradient vectors for all that, I'll have this as the gradient vector of my objective function. That will be -1 when I differentiate in terms of x1, and -3 when I differentiate in terms of x2. That's my vector. You know what? This is amazing, like so interesting. That's actually my C vector, as you might notice. Those coefficients, okay, compose my C vector. I just plot it as my vector. So starting at this point, I plot -1 in terms of this axis and -3 in terms of this axis. Take a look. I tried, of course, -1 over here from this point to the left, and -3, like 1, 2, 3, in terms of x2. And that's my vector, starting at this point and going to this particular point. That's a position vector representing my gradient for my objective function. I will plot the same vector on each corner. Sorry, guys, on each corner. After plotting those that same vector at each corner, I plot the gradients for the constraints. Take a look. My first constraint, I call it A1. That will be +1, -2, +1, -2. The second will be -1, -1. Take a look, -1, -1, the second. This is related to the constraint of my first variable. Why I use like the E vector here? Because that makes us remember the E vectors used in identity matrices. Because in this case, for variables, that will be the case, at least for this. x1 has to be greater than or equal to 0. I differentiate in terms of x1. I will have 1 and 0 in terms of x2. And x2 in terms of x1 will be 0. In terms of x2, it will be 1. I will plot, first of all, this vector, 1 minus 2. Take a look. 1 in terms of x, 1 in terms of x1, okay? So in terms of x1, I'll have from a given point, I just go 1 to the right, okay? And -2 in terms of x2, -2 positions down. So if you look over here, that will be my vector +1, -2, this vector over here, and it happens again here, okay? Happens again here. So -1 and +1, -2. Okay, +1, -2, this vector here. So this vector and this vector, they touch, of course, only my first constraint, which is this one, this line over here. This line over here, this function over here, okay, is going to be touched by this red vector here and this red vector here, which is related to A2, -1, -1. Take a look. -1 and -1. -1, -1. That's my vector. Red vector here and red vector here. Then I have my 1, 0. That, of course, will be a vector in terms of my space. In terms of my space, touching this constraint related to x1. That's why we've got here like 1, 0. So it will be this will be 1, 0. That's this vector here. Sorry, guys, this vector 1, 0 here, 1, 0 here. This vector is 0, 1, 0, 1. You know what you have after that? The solution happens happens only inside a convex cone defined by the constraint vectors and the optimization, the gradient vector of our objective function has to be inside such convex cone. I have a convex cone here using this red vector and this red vector over here. The convex cone is the same as multiplying this vector by some alpha that goes to infinity, and alpha has to be positive. And this by a beta, and beta is also positive, multiplying by some beta that's positive and goes to infinity. Take a look, this vector is inside. No, it's not. It's not inside this convex cone. So it's outside. Once we have a convex cone here, the convex cone, why it is convex, just to remember, because I started on this point and go with multiplying this vector to infinity, go with this vector to infinity, and inside this cone I can form any kind of other vector inside it. Here I could form any vector multiplying this by some alpha, positive alpha greater than or equal to 0, and this by some beta. I could form any kind of vector inside this region, but this is outside the region. And again, here multiplying this by some alpha and this by some beta, which are greater than or equal to 0, I could form any vector inside this region, of course, or over here, but my optimization, my objective function, the gradient lies outside. How could I make it go inside? Just impossible. So every time I have my gradient vector of my objective function lying inside my convex cone, I will have the solution. Is it inside over here? No. Is it inside over here? No. Is it inside here? No. Is it inside here? Yes, it is. Again, this vector is going to be multiplied by some positive alpha and this by some positive beta. Actually by some semi-positive alpha and semi-positive beta, because both could be equal to 0. When I multiply this by some positive and this by some negative, by some positive beta, what I'm going to do, I'm going to produce some vector that represents, that is equal to this vector. What I'm doing here is what Lagrange did. When I multiply this gradient of this constraint by some positive value, or a value equals to 0 at most, and this gradient vector of my constraint by another beta, which is greater than or equal to 0, I can make it equal to my constraint, to the gradient vector of my objective function. That's actually the foundation used by Lagrange to find Lagrange multipliers as we did before. So we have the gradient. I'm going to write like this. The gradient vector of my objective function is going to be equal to some, in this case, alpha multiplied by the gradient vector of my first constraint plus some beta multiplied by the gradient vector of the second constraint, and so on. This is why, and this is the origin of the Lagrange multipliers, as we discussed before. So we had to give like lots of steps to get back and understand, okay, so this is the origin of the Lagrange multipliers. So interesting, isn't it? And this is only possible for alpha and beta greater than or equal to 0. Because if we accepted negative values, this vector could be outside the cone, outside the convex cone. Remember, this is a convex cone because I can multiply this vector forever and goes to infinity, and this over here too, to form any vector that lies inside it. If we consider some vector outside the convex cone, what would be the problem? The problem would be that I would accept negative values for this vector and negative for this. I could form some values around on this side, on the other side, For example, positives and negatives, I could form a whole space. However, if I formed like if I had the complement of this convex cone, would be the rest of my space except the convex cone. So if I had one point here connecting to another point on the other side, the line would cross a region that is outside my space, my solution, my feasible region. Okay, this is quite interesting. This is really useful. That's why we have the solution for our problem. And there is something really, really interesting here. This is the origin of that minus sign. When we are solving a maximization problem, we use a minus sign we use the minus sign times the Cauchy-Tucker multipliers time constraints. And when it's a minimization problem, we use plus sign times Cauchy-Tucker multipliers times constraints. You know why? Because that will have an effect on this vector. That will make this vector change and bring it inside to my convex cone. I'm going to talk about this. If I had a maximization problem, take a look. The negative of the gradient lies inside my cone. So this is so interesting. Again, if I have a maximization problem, the negative of my gradient vector of the objective function lies inside the convex cone. So if I am considering a minimization problem, when I find the gradient vector of this optimization of this objective function, it will lie inside my convex cone defined by my constraints. When I have a maximization, it's the opposite. I had to either multiply my objective function by -1 to make this gradient vector lie inside, or if I prefer, I can multiply each of those constraints by minus some Cauchy-Tucker multiplier, and that will make a gradient of the objective function lie inside the convex cone. That's so amazing, so interesting. I really recommend you guys to think about this and bring your questions to to the office hours. Okay. I also invite you guys to study a little more on the forecast lemma. This book by Bazara, Jarvis, and Shirali, as I mentioned before, discusses on the forecast lemma. Please try to study it. Again, another important point. For this class, you implement the simplex tableau as we did before to solve problems. Of course, the problems have to be in the standard form. The standard form for the maximization and the standard form for the minimization. And then you solve. Of course, you're going to solve, and every time, every step you give, just think about the basis, about the solution you are finding, about of course, about everything you are doing when you solve your simplex tableau. Okay, bring your questions. See you guys in the next video.